Welcome to Lesson 6D, Evaporation, No Wind. We're going to talk about evaporation of pure liquids from some kind of open container into stagnant air, so there's no wind, and I'll do an example problem of it. Here's our setup. We have some kind of a liquid down at the bottom with a free surface, and then I'm plotting the partial pressure of that liquid. So right at the interface, it would be PJ1. I'm going to do this at Z1. At the surface would equal PVJ, which you can look up, vapor pressure. And then we're going to let Z2 be the top of the container. And for any cross-sectional area, A, so that's the area of the open surface there, we have some molar flux going across it. So let's make some assumptions and approximations, A and A. T is constant everywhere. P equal P atmosphere is constant everywhere. Both the vapors of the VOC and the air are ideal gases. It's quasi-steady, which means that when we're looking at this picture, it's steady, except we know that over a long time period, this surface is actually going to decrease because of the evaporation. But that's going so slowly that we can treat it as a steady process for these purposes. Z1 is the interface, Z2 is the top of the container. And I'm not going to derive any of these equations, but it turns out that the molar flux, which is what we want, is this coefficient Kg, which I'll define in a second here, times Pj1 minus Pj2. These are the partial pressures of the contaminant, or the VOC, of species J, where Kg is called the mass transfer coefficient. And it turns out that Kg is equal to dAj P, remember our binary diffusion coefficient. These are ideal gases, so we have the ideal gas constant Ru, universal gas constant, times T, that has to be in K, remember, not degrees C, Z2 minus Z1 Y AM. Or it's also equal to dAj over RUT, Z2 minus Z1 PAM. So there's two different expressions for this mass transfer coefficient, whether you want to work with partial pressures or with mole fractions. You take your pick. I'm going to typically use partial pressures. And then this is NJ. That's what we want, the molar flux. So I have to define these two guys. PAM is called the log mean partial pressure ratio of the air. A means air. It's given by PAM equal PA2 minus PA1 over natural log of PA2 divided by PA1, natural log, not a log base 10. And YAM is a similar thing. It's the log mean mole fraction of the air. It's defined the same way. YAM equal YA2 minus YA1 over natural log YA2 divided by YA1. Again, we'll predominantly use PAM, but you can also use YAM depending on which one of these equations you want to use. They're the same. And I just wanted to comment that you may recall log mean type things from heat transfer. When you have a tube and it has some heat transfer coming out of it, we defined a log mean temperature difference in heat transfer. This is the same idea. It's basically, these are like averages for an exponentially varying property. We have this kind of exponential looking curve here, and so this PAM is a kind of average for that exponential kind of property. My comments here, log means are a kind of average. PAM and YAM are for air, not species J. So make sure you're using the proper ones when you plug into equations. YAM is typically near 1, and PAM is typically near P atmosphere. We just call that P sometimes. Why? Because we generally have mostly air. The concentration of J is usually small. Even for highly volatile, we're not anywhere near half. We're like 10% or something would be considered high. So when you do the math with these PAM and YM, they turn out to be close to either 1 or P atmosphere. Also, these are related. YAM equal PAM over P. And that's kind of nice because it's just like first week of class when we said that yj is equal to pj over p. I'm happy about that. You can easily remember that. And you can see that from these two equations, if you compare these two equations, the only differences are here's PAM and YM, and there's a pressure in this one. So that agrees with what I just wrote. Now, the last thing we need to do is convert this to m dot j. So basically, just from units, we can figure this out. M dot j is nj times A times mj. So with our container, we have remember, some cross-sectional area A. We have this liquid that's evaporating. What we're really interested in is m dot j, which is the source strength or the mass flow rate of the contaminant into the air. These units are kilomole. Remember, it was per unit area per unit time. So kilomole per meter squared per second. That's the molar flux, meter squared. And then capital M molecular weight is kilogram per kilomole. And so these all become kilogram per second. And so if we combine all these equations together, we can get a summary of all equations that we'll need on equation sheet and below. Here's all the equations that we need directly from the equation sheet. Here's our final workhorse equation that we want for these kind of problems. It's the m dot j evaporation. We have equations for all of these variables here. You have to look up mj, ru is known, daj you have to look up, the pvs you have to look up to figure out this PAM, etc. So this will all be clear with an example. We have a standard 55-gallon drum, which has a cross-sectional area of 0.25 square meters. The height from the bottom to the top is 0.813 meters. We're going to use PERC as our liquid, a chemical that's commonly used for cleaning and stuff. The top is open to the atmosphere. Vapors are coming out. We have 20 degrees C air, which I immediately converted to Kelvin PSATP. Let's calculate the emission rate of PERC vapors into the room. I repeated all these equations here. We have to get MJ. I got that from the NIOSH pocket guide, 165.8 kilogram per kilomole. I need to get PVJ. Now here you have a choice. If you use table A.8 and interpolate, I showed you how to do that last time because 20 degrees C is not one of our numbers there. So if you interpolate, you get PVJ equal 14.96 millimeters of mercury. And if you use the NIOSH pocket guide, they just give it to 2 digits, 14 millimeters of mercury. Now, which one is better? Normally, if I interpolate from a good table, I'd say that the interpolated one was best. But since NIOSH gives these values at 20 degrees C, and linearly interpolating introduces some errors when it's not a very fine table, which it's not. So I would trust this one more.
But sir, it's only 2 significant digits.
Yes, BJ, but remember there's a difference between accuracy and precision. This one is more accurate, even though this one is more precise.
Thank you, sir.
DAJ comes from table 8.9, and I get 0.74 times 10 to the minus 5th meters squared per second. PJ1 is equal to PVJ. Remember, PJ1 would be the value right at the interface here, and that is equal to PVJ, 14 millimeters of mercury. And then, remember, we need PAs. These are partial pressures of the air up in this equation. So PA1 is equal to PA atmosphere minus PJ1 equal to P minus PJ1. Remember Dalton's law, sum of all the partial pressures must equal the total pressure. That's where I'm getting that from. So this is 760 minus 14 equals 746 millimeters of mercury is our PA1. PA2 is approximately P atmospheric or P. Why do I say that? It's because, again, when you plot these partial pressures, if you plot the partial pressure of the substance, this goes very small. So it's almost all air, and then the air one goes like this, and it almost becomes atmospheric pressure. We don't really know exactly what that'll be up there, so this is an approximation. PA2 equal 760 millimeters of mercury. From that, again, Dalton tells us that PJ2 is approximately 0. And then now we can plug in PAM, and this is just a matter of plugging into your calculator now, 753.98 millimeters of mercury. Now we have our final equation then, which is this m.j equation here, our workhorse equation. So I'm going to do this very carefully with all the units. We have everything we need now. m.j equals P, that's atmospheric pressure, 101.325 kPa. DAJ, we had looked that up, 0.74 times 10 to the negative 5 meters squared per second. PJ1 was 14 at the interface, minus, remember we approximated PJ2 as 0 millimeters of mercury. The area was 0.25 meters squared, and the molecular weight is 165.8 kilogram per kilomole divided by RU, 8.314 kilojoule per kilomole K, and then T, use Kelvin, 293.15 K, 0.813 meters is your delta Z, Z2 minus Z1. And then we just calculated up here, PAM, 753.98 millimeters of mercury. And then we need a couple unit conversions. Kilonewton per meter squared is a kPa, kilopascal, and a kilojoule is a kilonewton meter. If you cross everything out, all the units go away except kilograms and seconds. And to 2 digits, I get 2.9 times 10 to the minus 7th kilogram per second. So that's a very small number in terms of kilograms. That's why we often convert to milligrams per second. So this is our final answer. This is equal to the source strength due to evaporation.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.